Okay. All right. So good morning, everyone. Welcome to History of Astronomy 1. I plan on making this a kind of a year course. We'll focus here on the ancient Greek astronomy for this term, and we'll kind of lead right up into the late Middle Ages, right before the beginning of the Renaissance. Our course will try to cover that material from the very beginning up through that point of the late Middle Ages, getting us ready for the spring course, which would be the scientific revolution, going from Copernicus to Newton. So that's the plan for the year, and that's why this is called History of Astronomy 1. Today, what we want to focus on is actually the sky, some fundamental positional astronomy, because this is what the Greeks were trying to explain. And this is exactly what Galileo and Copernicus and Newton were trying to explain, what we see in the sky. So we need to make sure that we have a fairly good understanding of what it is that we see. If we were all farmers of 100 years ago, this class would be completely unnecessary. We would know the sky very, very well. But as modern people, with all the light pollution and everything, certainly people who live in the big cities have very little understanding of the sky. They can hardly see the sky. So it is important that we go through this stuff. Much of this stuff, many of you will know. I ask for your patience so that we all get on the same page, and let me go through this. And if you're not an amateur astronomer, if your knowledge of astronomy is just something kind of casual, well, I may even have a couple of surprises for you in terms of what I'm going to go over. So let us begin. We have the picture there to the left, the beautiful Orion constellation. Here's the sword of Orion, the belt. And here's Betelgeuse, and here's Rigel among the 10 brightest stars in the sky. And here is Sirius. Here is the brightest star in the sky. It's very easy to see when you see Orion, which is a winter constellation. Really, there are winter constellations and summer constellations. Yeah, we'll see that. The belt of Orion is very nicely points right to Sirius, where you can see that. Coming up this winter, we have the winter triangle as opposed to the summer triangle. The winter triangle is the brightest star in the sky, Sirius, and one of the corner of Orion, Betelgeuse, and another very, very bright star, Procyon. And here is Rigel here, and say these stars here are all in the top 10 brightest stars in our sky. And this guy here needs no introduction. Right? This is the most dramatic, I guess, astronomical thing that we can see from the Earth is a solar eclipse. Okay. As we know, all peoples have first of all studied the sky because the sun, every people's, no matter where you are on the spectrum of civilization or being primitive or not, everyone recognizes the sun is the giver of all life. Without the sun, there is no ball game. Every peoples recognizes that. And the night sky has always been studied because it's beautiful and because it is absolutely overpowering. And we don't see that so well in modern times. But if you go out west still, if you go out to Bryce Canyon and places like that, you can see the majesty and recall the majesty and the overpowering just spectacle of the night sky. So the night sky has always been studied by all peoples, no matter what level of sophistication they are on, from the most primitive hunter-gatherers all the way up, to the great civilizations of the ancient world, like Egypt and Babylon, China, Japan, the Aztecs, the Mayans, India, from the most primitive up to the most sophisticated, they all knew something about the sky. And they all wanted to understand where the sky came from, how we came from, how the world works, how the universe is put together. Everyone, again, tries to explain that in some way. And the first level of explanations we know are the great myths of the world. Um, Myths are beautiful, beautiful stories. There's certain kinds of truth in those stories, but they're not scientific stories. And what do I mean by that is they're not verifiable or falsifiable. They're complete and totally self-contained. They leave no loose ends. They describe what they want to describe completely. They tell you exactly everything you need to know about the question direct. How did it come to be that? Why is it that we see that the myths explain this completely? Okay. There's no quantitative description in any of the myths. Numbers are not used in any way. Mathematics is not used in any way. And most importantly, why I mean by it's unscientific and it raises no open questions, right? It explains everything. No further investigations are needed. This is the exact opposite of what a scientific theory does. A good scientific theory not only explains part of these phenomenon that we're studying, but it raises those important questions. It raises new problems that have to be pursued. That's what a good scientific theory will do. And so therefore we have the vector, which, brings science forward each day because of those open questions. The myths don't have any of those properties, as beautiful as they are, and as ubiquitous as they are in all peoples. They have those fundamental limitations that they do their job, and then we go on with the rest of living without actually having to pursue these questions. It completely satisfies the need to know at that level. And there are, say, great myths right throughout the world. I gave you a few to watch if you had the time. I hope you had the time to watch that 12-minute video of Crash Course on the creation myths. I think he posed it, very nicely, explained it much more thoroughly than what I just did here in those 2 minutes. I think it's a very interesting presentation. The Egyptian myth is the first one that I suggest you take a look at, and they all have a certain, theme to them. Let's take a look at the Egyptian myth together so we can just see what I mean about how it's self-contained and there are no open questions left once the myth is told to you. So let's take a look at that. Sorry about this, but we know this is unavoidable. Okay. Okay, so see that and the other myths that I suggested in the email all have that same basic theme. There's a beginning of chaos, and what the gods do is to create order for us, for man, create us, create the world as we know it. And very important element of it is that they create order in the universe. That particularly the myths of the very advanced civilizations who recognize that there is great order in the universe, and we're going to take a look at that order this morning with the patterns of the sky. There's a great difference, as we know, between a hunter-gatherer society and an agricultural society. It is the agricultural societies who are bound to the land. They live in one place, they don't move. And they have an incentive to build large structures, permanent structures. They have an incentive to measure the land, to divide the land. They have the ability to grow in their population way beyond the size of any hunter-gatherer society. They can become very large populations. Eventually, we're talking about having cities, and from that, the great civilizations. This is a great development in a sense in the history of humankind, to move into this agricultural environment and then begin to build what we call, for better or for worse, civilization. And that just can grow and grow until we have the kind of great examples that I'm showing here. Vast cities and empires with tremendous organizational issues. And these societies require a different kind of mechanism to survive compared to a hunter-gatherer society. And among many, one which is very important is to be able to keep records, to actually keep written records. There is so much information that needs to be known to run a society like this, to function in a society like this. Not only do records have to be kept, but many of these records are mathematical, they're numeric records, and therefore the growth of mathematics. This is all part and parcel of the great societies, which we see in every society, right? Not only the ones that we're familiar with in the West, in Egypt and Mesopotamia, but again, the Chinese, the Japanese, the Indian, the Aztec, the Mayan, they all have this characteristic of, if you're going to grow a sophisticated society like this, you need to cross this threshold of keeping records, of having mathematics. And you can see the reasons here, for reasons for commerce, reasons for just government administration, taxes, census, divisions of land gives rise to elementary geometry. Having large armies requires all kinds of record keeping and mathematics. And finally, astronomy and religious practices, which grow up together in these societies by and large. Most societies, the first astronomers were the priests, or a segment of the priests that were charged with watching the sky, creating a calendar, keeping a calendar, etc. And so this is, one of the great revolutions really in the history of the world, is to go from a hunter-gatherer type society to an agricultural society. And that agricultural society can really just continue to grow, like I say, for better or for worse, to what we have today. And when we look at, again, focusing on, the history of the West, which is what our focus is, because we're moving towards the astronomy of the ancient Greeks, because they are the foundation of the scientific revolution, because the Western scientific revolution is the foundation of modern science. That's why we're focusing, our story, of course, exclusively on the West. Here is just a list of the technology developments from the administration, the running of these great societies. And as you look down, a few that are of great interest to us is the measurement ones, like the scales and the sundials, okay? The calendar, of course, maps, mathematical texts, medical texts, Of course, the alphabet, okay, clocks, okay. These things are very old. They've been around a long, long time. And they were used by what I'm calling the sky watchers, the people who watch the sky every day and every night. That was their job. And they began to keep records, numeric records, sighting records, observations, and these were handed down from generation to generation. And this is how the patterns emerged. This is where they began to see the real patterns, way beyond the vague patterns that are needed in a hunter-gatherer society. These are detailed mathematical records. For example, in 2800 BC, Egypt has a calendar of 365 days. You wouldn't be impressed with that. Oh my God, how could they figure out that the year is 365 days? How would they know that way back then? Well, see, it's not that hard. It's not that hard if you keep records, if you watch every day. And not only for years and years, but for hundreds of years, for 1,000 years. And that's what they did. Eventually, you catch on as to just what's important and what's not important, and what records to keep, what records to take. And this stuff does naturally evolve over a long period of time. Just to have one bow towards the non-Western tradition, just take a look for a moment at the ancient Chinese astronomy and their dates. Back in 2000 BC, we have the records of solar eclipses. They knew that Jupiter took 12 years to complete one revolution around the sky. Now that talk about record keeping, right? Records so that they could see that it took 12 years to come back to the cycle where the record began to repeat itself. Okay? This is 2000 BC. Notice the constellations. The constellations are developed. All great societies have very detailed maps of the sky. We, of course, follow the constellations handed down mostly from the Babylonians, then to the Greeks, and then to the Romans. And finally, many of the names of the stars come from the great Arab culture during our dark ages. But all these records were also kept by all the other great civilizations. The spring equinox, here we have the beginnings of the calendar. And two which are interesting, we'll see next term. In 532 BC, a nova was recorded by the Chinese historians. The first nova recorded in Western history is by Tycho during the scientific revolution in the 1570s. In the 1570s, Tycho Brahe recorded the first nova. They saw one, and of course, novas happen, periodically, regularly, creation of a new star. Some reason the West never recorded a new star until Tycho, the great astronomer, saw one. And here in 384 BC, we have the earliest record of the observation of sunspots. In our history of Western astronomy, sunspots were discovered first by Galileo in 1610, when he had his initial telescope. You can see sunspots with the naked eye if you can create the right technology of mirrors and glass to do this. And apparently this was done long, long ago by the Chinese astronomers. So the history of astronomy around the world is a vast subject, which we cannot, touch. I just wanted to show one slide where there's a lot of astronomy that we are not going to talk about in different cultures, again, because our focus is to get to the great geometric models of the Greeks, because that's the model that Copernicus went ahead and overturned. Okay, just again, more slides on the Egyptian astronomy, again, seeing the record keeping, using the hieroglyphics, but the idea of keeping records, numeric records, and of course, the keeping of time and the keeping of the calendar. Most importantly for our story is the Babylonian astronomers, because after Alexander the Great, with the merger of Greek culture and the Babylonian culture, this is the beginning really of science as we know it after Alexander, the Hellenistic age. And so this tradition of this kind of record keeping, this kind of continuous record keeping by the Babylonians becomes very, very important. One of the most important legacies that's given to Greek culture once Alexander combines those empires, and we get the very easy flow of ideas from back and forth. And you can see, again, we have listings of planet positions and listings of eclipses. It's interesting that the Babylonians never actually created a real geometric model of the universe beyond simple kinds of myth pictures. They had no need really for that. These tables of data is really what they needed. They looked for their patterns in the tables, and they found the mathematical patterns so they could predict the next eclipse. They certainly could create the calendar by looking at records like this to know the solstice, the equinoxes, when to plant, when to sow, et cetera, et cetera. It was all done looking at the mathematical numeric patterns of the records that they kept for 1,000 years. Okay, they really did not need to create, they didn't feel the need to create a geometric model. Their geometry also was really not up to the task. We really need to wait for the Greek civilization to develop a geometry that could actually tackle the problem of what does the sky look like every single night. But what we do have here are these incredibly voluminous records. Ptolemy himself begins his calendar with around 700 BC, going back to these records. He uses these records to begin his data, to begin the ultimate geocentric model of the Greeks, the Ptolemaic system. He begins with these records here. And so, again, just to look at the contribution of the Babylonian astronomers, because this is the great legacy which is handed to the ancient Greeks. These records do represent the oldest systematic data records that we have across all societies. Okay, these are the oldest. Certainly records were kept in China and Japan and the Aztecs, but nothing is older. We have nothing that comes down to us through archaeology that is older than these records. And the Babylonians are the ones that give us the 360 degrees in a circle, 360 60 minutes in each degree, dividing the day and night into 12 pieces, the 24-hour day, and giving us the 12 sections of the sky of the zodiac that we still use. All these things were given to us, given to the ancient Greeks by the Babylonians. And they, by the way, very much admitted that. They admitted that they learned a lot from the Egyptians and from the Babylonians in terms of their mathematics, the crude mathematics that they had, and the astronomy. Okay, so let us begin. Let us begin to look at these patterns of the sky. Do we have any questions so far? Would you like to unmute yourself, anyone, with a question? Okay, I'll take that as a no. Are we still here? Are you with me? Mike, can you unmute yourself and tell me that we're all still here?
I think we are.
Yeah. Okay. It's a little weird teaching remotely. All I'm looking at is a stupid screen and I don't see you guys. Thank you, Mike.
This slide that you have up right now tells me that the question I was going to ask may be covered. I was thinking, if I were trying to figure out that a year is 365 days long, maybe one way I would do that is to keep track of how long the day was.
Yes.
And then measure when the shortest day recurred.
Very good.
I'm wondering if that's what they did.
Yeah, absolutely. That's what we're coming to. That's exactly where we're going. That's exactly where we're going, Mike. So let's go ahead and continue on with this. And here, of course, undoubtedly, right, is the fundamental cycle of the world. This is our fundamental cycle. Okay, the rising of the sun, going across the sky every day, allowing us to live, and then the night, the dark night, where you can't, see anything without artificial light, and all the stories of the night. This is our fundamental cycle of all peoples, of all times. The moon are important, right? The phases of the moon. It's something that all peoples, of course, notice. It's so dramatic. So many of the early calendars were not solar calendars, they were lunar calendars, because the moon goes through its phases every month, every 30 days. So it's maybe easier to keep track of a calendar every 30 days than to get that 365-day cycle. So many hunter-gatherer societies, for example, have a lunar calendar as opposed to the solar calendar. It's the agricultural societies that really need a solar calendar. The lunar calendar really is not enough because it doesn't take into consideration the changing of the seasons. And of course, we have the patterns of the sky. Okay, and let us take a look at that. Let us take a look at the patterns of the sky. This is a wonderful video. This is something that you can watch more than once. I think you really enjoy this. Here's the sky, Arizona, and we're first of all, we'll be looking west. And here we're looking west, we see that the stars set in the west, just as the sun sets in the west. I don't know if you can see up in the corner by little mini-me. Can you see up in the corner, up in little mini-me? Things are not changing so much up there. Yeah, that's Polaris, right? There's the fixed star. Now we look east. And yes, the stars rise in the east, just like the sun and the moon and the planets. The sky rises in the east. Here's Orion here, okay? And here is the belt, and here is Sirius, the great goddess of the Egyptian myths. We look north, and now I think it's easy to see that central point. Huh? There is Polaris right here. Polaris does not move. The whole sky seems to turn around it. And finally, this is where the action is, where we look south. As we all know as drivers, the sun is in the south of the sky. It moves from east to west, but it is just south in the sky. And this is where our action is, where the planets are. Here is Orion here, his Betelgeuse, his Rigel, here's the sword. Here's the belt of Orion going down to the brightest star in the sky. Here's Sirius, here's the Pleiades up here, okay? And a beautiful picture of probably the most beautiful constellation, Orion. But take a look, this is the brightest star in the sky. This is Sirius, right? This is the god Isis of ancient Egypt. This is the queen of all the gods, Sirius. Take a look. Compare Sirius, the brightest star in the sky. Of course, we have the Milky Way. But take a look here, what's coming up the east. Yeah, look at that star. And that star. Compare these two stars to the brightest regular star in the sky. What are these two great lights, right? These are the planets. Right? The planets are, when they're bright, the brightest stars in the sky. This is Jupiter here, and this is Venus. Venus is the brightest star in the sky, always. Venus is always the brightest star in the sky, no matter what disposition it is in. So you can see, this is where our action is looking south. We'll always be looking south when we take a look at the sky in real time, because this is where the moon is. This is where the sun will come up in the east and go over to the west, etc. So, southern sky. Okay. So the discovery of the order of nature. When was this discovered? Well, it's lost back in history, and all great civilizations have discovered this order. But the order is the same. The order that we find in nature, the fundamental order of the sky, is the cyclic motion of the sun over one day. Every day we get the same cycle, and over a year, there is a yearly cycle for the motion of the sun. The cyclic motion of the volt of the stars over one night, and again over a year. The stars come out at night and move throughout each night, but yet over the whole year, there is a recurring pattern. The cyclic appearance and the motion of the moon over 1 month. And finally, the complex and individual motions of the 5 wandering stars, the planets. And this is the problem that needs to be solved, right? If you're going to build a model of the sky, the sun, the moon, and the regular stars, the fixed stars, they're not so tough. You can do that fairly easily because their motions are fairly regular. A little bit of head scratching, you can figure something out. It's the motion of the planets that will make you crazy. Where is the pattern here? What is going? How do I find a mathematical description that can create this kind of complex motion? 5 different motions going on simultaneously, as we'll see. This is the great problem of astronomy. So we go back to the beginning. We go back to sunrise and sunset. Mike's idea. One way is you could look at the length of the day. That's a very nice idea. Another one is you could just watch the horizon. Okay. I apologize to you New Englanders. I am a born and raised New Yorker, born and raised up the hill from Yankee Stadium. I apologize for all of that, but now I'm down in Pennsylvania. So, but this is a great picture in Manhattan of the sun rising and going right across 34th Street, at the Empire State Building. And yeah, we know that the sun does not rise right there every day, that the sun moves back and forth across the horizon. One way that you could measure the year is to wait for that to happen again. It'll happen about 6 months from now, and it'll finally happen a second time back in the same season. And that's another way to count 365 days. So here is the sunrise here, and here is the sunset. Where again, the sun sets differently across the horizon. You will be surprised, as people living in rural New Hampshire, you know these things, of course. You will be surprised how many people in Manhattan and Boston don't know this, because they don't see the sun very well out their window in the morning, and they don't notice the sky. They don't need to notice the sky. They live in such an artificial environment. One of the wonderful things that we experienced and enjoyed in retiring up to you guys 12 years ago was that we saw nature so much more than we ever did in New York. And so it is you might be surprised about the ignorance of people in a big city that have with the sky, because for one thing, they just don't see it. And to get back to our sky watches, to really watch the sky, to keep records of what the sun is doing, and it's all in the shadows. It's all in the shadows that the sun makes. Here we have Stonehenge going back 2000, 3000 BC, and a beautiful Chinese sundial, right, where the gnomon is missing, but you can see already to track the shadows of the sky. And so let's take a look at that. Okay, what do the sky watchers see when they watch the sun every day? Every day, day in and day out, not for years, not for 100 years, 500 years. They keep records every single day. What do they see? Okay. They see the sun come up from a certain direction on the horizon, and they watch the gnomon, the shadow, the length, get shorter and shorter because the sun is getting higher and higher. It reaches its shortest shadow, therefore its highest point, and then it sets down on the other side of the horizon. And this happens every single day. Okay. Watching the length of that shadow will tell us exactly where the sun is at its highest, the shortest shadow that day. What's remarkable, the first great piece of order that you see, that not only does the cycle repeat itself every single day, And there are changes. The sun does not always come up in the same place on the horizon. It moves back and forth as the year goes on from the horizon. But by the way, we're looking here to the south. So this is east. Right? Since we're looking south, east is to the left and west is to the right, because we're looking to the south, not to the north. So the sun rises in the east, goes over and sets in the west. So we know that the sun moves back and forth during the day. Sometimes it rises more southerly, sometimes it rises more northernly. But what's interesting is if you watch the shadow every single day, the shadow will have different lengths, because we know that the sun is higher in the summer than it is in the winter. The sun will be much higher in the summer, and so the shadow will be shorter, and the sun has a much lower trajectory, rising in the south has a much lower trajectory, and it's lower in the sky, so the shadow will be longer in the winter. But what's amazing is that the highest point, the point where the shadow is the shortest, is always on the same line. It creates a line in the sand. Every day, no matter what the height of no matter where the shadow is at its highest, the point of that highest shadow, the shortest shadow, the highest elevation of the sun, lies along the same line. And that is the sun telling us where east and west is, right? It is, where north and south is. The line is pointing towards us, that is due north, and pointing away from us, that is due south. North-south is not some line drawn on a map. The sun tells us exactly where north and south are. And as we know, the sun moves back and forth. And so there's one particular day, or two particular days, in which we have, where are we? We have this phenomenon. I'm sorry. I think I did not mark my, well, let's take a look at this. We know that as we look throughout the whole year, we can see that there is a particular day in which the sun comes up, goes across this green trajectory. It has a particular shadow. All the shadows lie on the same north-south line. But this is the particular day that the trajectory has it so that the amount of daylight that the sun is up on the day is exactly the same as the amount of nighttime. Here, as we move towards the warmer and warmer, getting towards the summertime, as we move north, here the trajectory is much longer. So we have a much longer day. We have a higher highest elevation. We have a longer day than 12 hours. And as we move back towards that equinox day where the sun is equal in day and night, we continue on and the sun will move in the other direction along the horizon, getting towards the winter, in which the sun will rise more in the south and will be a much shorter trajectory, a much lower trajectory, and that shadow will be much longer. And here we're looking at the cycle of the sun. I think I finally can see where the animation I wanted to show. Yeah. So here is the equinox here, where the sun rises exactly in what we now call due east and sets due west. Why? For two reasons. One, it's in the middle of that whole arc from the summertime to the wintertime, that whole arc on the horizon of how the sun comes up. This is the one right in the middle, both on the rising side and on the setting side. Okay. This is the day where the amount of time that the sun is up above the horizon is exactly equal to the amount of time that we don't see the sun, that we have the nighttime. This is called the equinox for that reason, the equalness of day and night. The equinox, by the way, guys, is tomorrow, September 23rd this year. And again, even though this shadow is for this particular one, okay, is for the equinox, it's still all of the shadows, all the shortest shadows, all lie along the north-south line. Quite an amazing piece of geometry that the sun gives us. And finally, we have this, this picture here. Okay. I think I can close Mathematica now. I think I'm finished with Mathematica. Let's go back and just review what we've said here about the motion of the sun. So the sun changes its highest elevation, going from the summertime at its highest down to the middle range of the equinox, down to the lowest elevation in the wintertime. And as that elevation changes, also the place where it rises and sets on the horizon also moves in tandem, where it rises very much in the north in the summertime for a very long trajectory. It's in the sky for a long time. But since the sun is in the south, if it rises in the south, it's not going to have a very long time in the sky. It's going to be low in the sky in the wintertime. And here's just another view of that time. Here we have the first day of winter, where we have a very short day and a low highest elevation. Here is the equinox, where we have that middle range day, where the middle range of the elevation, and finally we have the first day of summer, which is the longest day and the highest elevation. And again, the moving of the sun back and forth along the horizon as this is all happening. And this beautiful dance of the sun is something that all the sky watchers were able to record with incredible accuracy. And so it is not surprising that the Egyptians in 2000 BC, or wherever that was, have an accurate calendar of 365. Actually, they had figured it out to be 365.25 days. They knew about the quarter by looking at the stars as well. And just going back to Mike's idea, here are the times. Here are the daylight times. This is the first day of winter. This is the lowest. The sun is in the sky for about 9 hours, and it gets longer and longer and longer until we reach the equinox, where the sun is in the sky for 12 hours. And then as we move towards summer, the days get longer and longer and longer, where the sun is finally in the sky at its peak at 15.33 hours. And after we pass the first day of summer, the days begin to grow shorter and shorter and shorter until we reach the fall equinox, where we go back to tomorrow, where the sun will be in the sky for 12 hours again. And then we'll continue on into the winter, where we go back to the shorter and shorter days, and we start the cycle all over again. And if you count that number of days, as Mike suggested, you will get 365 days. And here is another way to visualize this. This is anachronistic. We won't see these kinds of pictures really until the late Middle Ages. This kind of visualization. The ancients really did not do data like this. They really worked from tables. They looked for their patterns in tables. They did not draw data graphs like this. This comes in the late Middle Ages, right before the Renaissance. But again, we see here the beautiful geometry, the symmetry here. This is an upside down sine curve. Essentially, we go from the first day of summer of only 9 hours up to the equinox, and then the longest day up in the summer, first day of summer, the summer solstice, the fall equinox. We've explained why we have the word equinox. Equinox is because the day and the night are equal. What is the solstice? That is when the sun stands still on the horizon. And the most important day in all agricultural societies is the winter solstice, because each day the sun is rising more and more to the south, and the sun is getting weaker and weaker, and it's in the sky lower and lower and shorter and shorter. The sky is diminishing and diminishing and diminishing every day until finally we reach the winter solstice, and the sun stops and begins to come back again and begins to rise in the sky again. And this is December 21st. And all societies, particularly all agricultural societies, no matter what its level of sophistication, this is one of the most important days in their calendar, the day that finally the sun we know will come back and not disappear on us altogether, in which then we will all die. So the winter solstice, the stopping of the sun. It's interesting if you count the days, and of course the sky watchers do count the days. It's interesting that between the spring equinox and the fall equinox, we have a rather long period, right, of 187 days, whereas from the fall equinox around to the spring equinox, it's only 89 and 89, which is 90, 100, 178 days. Why is this cycle, this half cycle, so much shorter than this half cycle? There's all kinds of questions that will come up when you start taking records. You would think that they would all be even. But in fact, when you take the records over hundreds of years, you discover no, that they're not. And so these are beginning of the questions that can be raised to try to answer these questions. These questions would never come up, right, in the worlds of myths. You don't even have this level of detail. And finally, a beautiful picture of the sun, time-lapse picture of the sun. And there, that north-south line, by the way, is called the meridian. It is the most important reference point in observational astronomy. It's where we stand. Okay? It's where that shadow will come right at you, where the sun will come right at you at what's called local noon. And there is the sun every day rising at different elevations, but it rises at the same place, okay? So that shadow lies. So this meridian line, if you take that north-south line, guys, and take a wire and just flip the wire directly up over your head, and when the sun is at local noon, let that shadow, that wire, lie right along the north-south line. That is your meridian, okay? It is basically our line of longitude thrown up to the sky, okay? And this is the place where the sun always reaches its highest point every single day. And what we know, of course, is that given the times laid out by the Babylonians, inherited by the Greeks and the Romans, we have a 24-hour day. And so the sun moves from meridian to the meridian the next day in 24 hours. It moves 360 degrees in 24 hours. The sun moves across the sky at about 15 degrees every hour, 15 degrees every 60 minutes. 60 minutes, again, coming from the Babylonians. This is all protocols and standards that we have adopted ever since. 15 degrees every 60 minutes. Well, that's a quarter of a degree every minute, right? 15 over 60. That's 1 degree every 4 minutes. The sun moves across the sky 1 degree every 4 minutes, okay? Let's remember that. That'll become important, that the sun moves across the sky 1 degree in that circle every 4 minutes. The sun actually doesn't lie along the line exactly every single day. Instead, it produces this beautiful pattern, the analemma, okay? For primitive peoples, this is close enough. Without a telescope, without a very good sighting equipment, this will look like the same basic line every single day. Yes, actually, the very sophisticated societies will notice the analemma. They will have their equipment and their measuring sticks well enough to see the slight variation. But for us, let us not worry about the analemma. Let us think that by and large, the sun moves up and down, in a straight line. The analemma is, of course, explained by the tilt of the Earth as it moves around the sun, tilting in different directions. But by and large, we will, take the sun moving up and down that straight meridian line. This, of course, is very much the first day of winter. Looks like we're a couple of days off of the first day of winter, because the lowest point here, right, would be the first day of winter Here's the first day of summer. This is not the equinox. The equinox is actually in the middle. This is not the equinox, as it turns out, where it crosses. Of course, real positional astronomy is incredibly complicated. This is not a course in positional astronomy. We're trying to just get the fundamentals, the basics, the overall idea, so that when we start talking about the geometric models of the Greeks, we'll have some semblance of what it is they're trying to produce. But studying these things is really a different course. It's really a course for Claudio and teaching true astronomy. We don't have time for that. All we can do is look at the fundamentals so we can move on to our geometric models of the ancient Greeks. So there are very beautiful symmetries that we have. Talk about order. Okay? Look at the red words here. The shortest daylight and the longest maximum elevation, and the lowest maximum elevation and the most southern rise of the set points occur on the winter solstice. Okay? And I could have thrown in there, this is the longest shadow. And the longest daylight and the highest maximum elevation and the most northerly rise along the horizon occurs on the summer solstice. So the beautiful symmetry of the winter solstice and the summer solstice. Shortest, longest, lowest, highest, southern, northern, winter, summer. The order of nature. On the spring and fall equinox, the length of the day and the night are exactly equal. There's a beautiful symmetry there. And the rise and set points are the same. Okay? They create this imaginary line. If you were to draw a line from where the sun rises on the equinox to where the line sets, you get a line which is perpendicular to the north-south line. You get a line perpendicular to the meridian. Yeah, God is a geometer. This is a 90-degree angle. Okay, the sun creates a 90-degree angle with the line it creates at noon. This is the geometry of the sun. And we, of course, call this line due east and due west. So here we have the winter trajectory, the very short day. Here would be the equinox, the equal day, and finally, even coming up here from the north would even be a higher, longer trajectory where the sun is in the sky even for longer than 12 hours. Okay, so we now move on to the night sky. How are we doing with time? Questions? Anybody have any questions about the sun? I realize for most of you, you know this. This is very familiar stuff, but it's important to review it. Any questions?
Peter,
Yes.
if you go back to the previous slide,
Yes.
just something that visually appealed to me, the two, I'm going to call them hoops.
Yes.
The one for summer, the one for winter. Do they ever touch at any point? Do those two circles ever come together, those two half circles, if you extend them out?
No, they really don't. They're two very different trajectories. The middle one there is the equinox one where it rises due east.
Right.
The summer one would even be further away. No, these are these. I'm sorry. Are you asking, does the sun be in the same place in the sky during different days? Yes, the sun will get close to each other, in the different days, but they basically have these really separate arcs because of the varying elevation of the sun.
I was just imagining if those two arcs were completed and became circles or ovals or whatever, would they ever touch?
No, they
Just
will
a
never
visual
touch.
question.
Right, no, they would never touch.
Okay.
And I think one of the great advances of, you ask an interesting question, you make an interesting observation. Who am I talking to, by the way?
Jim Talbert.
Jim, you make an interesting observation, Jim, that it took a long time for people to realize that, in fact, the sun did go underneath the earth, right? The Egyptians had the sun going into the great river, and the gods would put Ra, on a gondola and bring him around the great river during night so he'd be ready to start his voyage the next morning. The idea of the sun actually going around the earth, this geometric idea, took a long time for this to develop. This was not developed until the Greek civilization put this forth. But in fact, these circles would be separate, even the paths going around the earth. Okay, so we move now to the motion of the sky. We're looking north, right? Looking at the North Star, Polaris. Okay, and we see that the sky, the night sky, is also in constant motion with these sun trails. If you're looking north now, right now, this is east over here. I'm sorry, this is east over here, and this is west when we look north. So the sky is turning this way. It's turning counterclockwise. It rises in the east, moves across the sky, and sets in the west when we're looking north. Most of the time, we're going to be looking south. Okay, so here's that picture. Looking north again, here is our meridian. Here's that wire, the north-south line on the ground that we threw up over our heads. And this is the wire. This is what it looks like up in the sky. And what is amazing, you should be amazed, I'm amazed every time I see this, that the fixed star, Polaris, is on the meridian. It exactly divides the sky in half. This line that the sun makes at noon every day is where Polaris is, where the North Star is in the sky. The same line, continuous line. You just go up from the ground and start going up on the horizon and just draw it in the sky. And that is that line there. And that is where Polaris is every night. The sun goes up and down in its elevation, Polaris does not. And as long as you stay in the same place every night, don't move around the world, Polaris will be in the same place every night, the meridian. Okay. So the dome of the sky seems to rotate about a fixed point, which lies on the meridian. Some stars are so close to that Polaris that they actually stay above the horizon all night. They're called the circumpolar stars. Probably the most famous would be the constellations of the Big Dipper and beautiful Cassiopeia, the great W in the sky. Many stars circle the dome in such wide circles that they actually appear to rise in the east and set in the west because the circle that they're making is so big. And here's the kicker. Here's the most important one. Here's the most consequential observation of positional astronomy. Not the most fundamental, but the most consequential. The time for any star to make a complete revolution of the sky from meridian to meridian is not 24 hours. Now, I would not be surprised if some of you are surprised by that. We know that the sun goes from meridian to meridian in 24 hours, but in fact, the sky turns a little bit faster. It turns 4 minutes faster every day. And that is going to turn out to be of tremendous consequence for us. And what we're going to have to accommodate these 4 minutes in building our geometric models. And this, of course, will be all the geometric models that we build right up through Kepler's laws, and finally with Newton's laws of gravity. This 4 minutes is so consequential. Remember, I asked you to remember that 4 minutes, the 4 minutes of the motion of the sky. The sky moves 1 degree every 4 minutes. And here we have the sky, the stars, moving a little bit faster than the sun by 1 degree. A coincidence? No, of course not. But it'll take a while for us to explain this. But it's important that we join the sky watchers and recognize it and see it in our records. Okay, I'm going to take a look at Solarium. Instead of running a new Solarium, allow me to get my old Solarium that I've got set up for us. So here is our Solarium. I want to it's not so easy to see. There it is. Okay. So here we are today, guys. Take a look down here. I've got Boston a nice, easy place for solarium to find. Here's our time. This is November 22nd at 9:34, okay? And we're looking south. Right? We always want to look south because this is where the sun is. And we can let, so by the magic of solarium, we can let the times move and we can come to local noon where the sun reaches the meridian. Okay, and that'll be today at 12:36. Yeah, it's not 12 o'clock. The clock on the wall, guys, is an incredibly complex piece of equipment. It's maintained by the Bureau of Standards in Boulder and by the people in Paris. And what the clock really reads at different places, incredible. That is a whole science in itself. But for agrarian peoples, for our purposes, for ancient peoples, this is noon, local noon there in our world. And of course, we know the next day we'll be right back. Go ahead and bring up our clock. Hello, clock. Here we are at the 22nd. Let's just go at 12 noon, 12:37. Let's just go one day. Okay, we're where we are. Notice the sun went down because we were heading into winter, right? The sun is at this elevation. Tomorrow, it'll be at this elevation and at this elevation. We know the sun is going down lower and lower as we go towards, as we go into the winter. That stick, the gnomon, the shadow is getting longer and longer. But what we're interested in, let's go back to today, okay? Back to the 22nd. What we're interested in is looking at the night sky. So let us go ahead and get to the night sky, a little bit more solarium magic. We'll let the sun do its thing. We'll let the stars come out, okay? And here we are at 8 o'clock in the evening. And we could take Altair, but it's very, very high up and not easy to see. So let's take Saturn. Saturn is not a fixed star. I understand it is a planet, but it takes 30 years for Saturn to get around the sky, guys. 30 years. Saturn does not move in one night. Trust me. Saturn does not, you will not see Saturn move in a week into the naked eye. You won't see Saturn move in the sky in 2 weeks. It takes a telescope to see Saturn moving. So Saturn is a better option for us because it's nice in the middle. So let us do a little bit more magic here. We'll let Saturn move along to the meridian. Okay, and here we are on the meridian, and the time here is 22:05. This will happen, Saturn will be on the meridian tonight at 10 o'clock, 10:05. Saturn will be on our meridian here. By the way, I have the same basic meridian where I am, as long as we have the same longitude, pretty much due south of you guys, about 300 miles. Let us see when Saturn comes back to the meridian. 22:05. Can we remember 22:05? 10:05. Let us go ahead and turn a day. The sky, the sun will rise, go across the sky, the sun will set, the stars will come out, and here is Saturn. Let us see when Saturn comes across the meridian again. Oh, sorry. Okay, try this once more, guys. Saturn will cross the meridian here. Okay. Take a look at the time. It is 22, I don't know if you can see it here. It is 22:01, not 22:05. It is 22:01. It is 4 minutes shorter than 22:05. The sky, the stars turn around 4 minutes faster than the sun. But our day is governed by the sun. Our day is 24 hours. That's how we live our life. That's how we take our records. So what is the sky going to look like the next day, right? This is now the night, 23rd. This is tonight. Let's go to the 24th. Let's go one day. Yeah, we will have moved, the sky will have moved 1 degree. Why? Because it only took 23 hours and 56 minutes to get back to the meridian. We have 4 more minutes. How far does the sky turn in 1 minute? I'm sorry, in 4 minutes, 1 degree, because it travels 15 degrees every hour, because it travels 365 degrees every 24 hours. It turns 1 degree every 4 minutes. The sky has 4 minutes to play with before it gets to 24 hours. It turns 1 degree. And the next day, and the next day, and the next day, the whole sky is turning every single night. Okay, here we're up to the 27th of October, sometime next week. Look where we're between Capricorn and Aquarius, okay, the meridian. Let's jump a month. Let's jump 30 degrees. Capricorn is on one side of the meridian, Aquarius is on the other. Here's Sagittarius down here. Let's go from 9 to 10. Let's jump a month. Here's Capricorn and Aquarius. They're both on the other side of the meridian. Here's Saturn way over here. Look how far it's moved. At the same time, we're still at 10 o'clock, guys. It's still 10 o'clock at night. It's just the sky has totally moved by 30 degrees 30 days from now at 10 o'clock. Okay? So this is why we have winter constellations and summer constellations, because of this 4 minutes. It's that 4 minute gap. It's the fact that the sky turns 4 minutes faster than the sun. And it's the sun that allows us to see the sky. It is the sun that allows us to see the night sky. It's the 24-hour cycle that allows us to see the dark sky. And what it allows us to see, when we finally see it, it has turned an extra 4 minutes. And so the whole sky is turning on us. And therefore, if it moves, 4 minutes, 330 degrees every month, it's going to take 12 times 30, it's 360, no? If it moves 30 degrees every month, yeah, it's going to move 360 degrees in 12 months, and that's our year. Fundamental year of the sky changing every year, okay? And before we leave Solarium, before we finish for the day, let's find the moon. Let's see if we can find that pesky moon. What do I want to do? Let's go forward a few hours. Can we find the moon? Hello, moon, are you around? I know we were near the new moon. I'm looking for the moon. Yeah, hello, sun. Where's the moon? Ah, here's the moon here. Okay. So the moon is setting here, so we need to go back. Go forward. Okay, here we are on October 28th. Watch the moon. The moon is on this side of the meridian. Let's go to the 29th. The moon has jumped from here to here. It's jumped from Scorpio into Sagittarius. Let's go to the October 30th. We're here in Sagittarius. We're still on this side of the meridian. The moon is jumping 12 degrees, as it turns out, every day. Why? Because the moon is slow. The moon takes not only 23 hours and 56 minutes to get around, it takes an extra 50 minutes to get around. The moon is much slower than the stars. So Sagittarius takes 23 hours and 56 minutes to get here. The moon will take 24 hours and 50 minutes to get here. So where is it in 24 hours? Where is it 50 minutes before that? It's back here somewhere. It's falling behind the stars. It can't keep up with the stars. It takes an additional 50 minutes to get back to the meridian. And so therefore it moves 12 degrees backwards every day with respect to the stars. Why do I say backwards? Because the whole sky moves from east to west, right? We're looking south. East is on your left. West is on your right. Look at the moon. The moon is moving east. We know it rises in the east and moves to the west, but it's moving backwards. It's moving eastward each night because it can't keep up. Sagittarius, Capricorn, Aquarius, it's moving through the stars, 12 degrees every night. 12 degrees every night, 12 into 360 is son of a gun, 30. It'll take 30 days for the moon to go all the way around the stars, and that's our month. Okay, there's a lot here. It's getting, I realize I'm throwing a lot. Let me stop here. Okay. It's a large presentation. We will finish it next week and go on to begin the beginnings of natural philosophy. But we wanted to go through this stuff slowly, and we certainly now want to take a look at the motion of the stars. I'm sorry, of the sun through the sky, and most importantly, a final look, beginning look, not a final look, a beginning look of the planets through the sky. Okay, so I will stop here and take some questions.
Well, Peter, I have I guess you might say cultural or sociological question, which you may say, boy, that doesn't interest me, or, I don't know anything about that, and you won't hurt my feelings if you say that. But I was intrigued by what you said about the Babylonians being data oriented, while the Egyptians and the Greeks were more graphically or visually oriented in their analysis of astronomy. And I wonder if that's a pattern of data perception versus visual perception that is considered like a cultural standard across many disciplines.
This has been talked about a lot, as you can imagine, by historians of science and, social sciences that study culture, anthropologists. These are different characteristics, definitely, of societies. And the Babylonian society was much more numeric oriented, whereas the Greeks, and we'll see why, the Greeks, their mathematics was anchored in their geometry, not so much in their arithmetic. And this is why, one reason why they never developed an algebra, because their mathematics was primarily geometric. The Egyptians were kind of in the middle. They really, didn't, they didn't do geometry nearly as well as the Greeks, although the Greeks will tell you that they learned their geometry, their initial element geometry, from the Egyptians, and they certainly did not take numeric records as accurately as the Babylonians. So there are these cultural differences. Now, it's a very, very interesting insight that's well known to anthropologists. Any other questions? All right, guys. Well, we're off to a good start. Like I say, what we're heading for, the end of this presentation, is the motion of the planets. The joke is that to solve the problem of the planets, to build a geometric model of the planets, God didn't make it impossible to do, but he made it difficult to do. He made it the problem so that you needed to invent algebra, geometry, trigonometry, and calculus in order to solve the problem. And although it is a kind of a silly thing, there's a lot of truth in it. And so much of our mathematics comes from the development of astronomy here through the scientific revolution. Okay, guys, so I will end the recording, and we'll see you next week.
Take care.
Okay.